I hope we all did our homework last night. Red, can you tell me what the FTC is? Red? Red!
Huh? What? FTC? I don't know anything about the Federal Trade Commission.
No, Red, not that FTC. The Fundamental Theorem of Calculus.
The derivative with respect to x of the integral from a to x of f of t dt equals f of x.
Good, that's part one. Moving on.
But Mr. Tweets, why is that true?
You don't need to know that, Red.
Hey, Red, what's the matter with you?
I just don't get this. It's the fundamental theorem of calculus, so it must be pretty important.
Red, did you not do your homework? It was all about how to apply the FTC.
No, I mean, I don't know where it comes from and why it works.
Oh, I can help you with that.
Oh, yeah?
Have I ever told you about the goals of rectan?
Eggy, are you messing with me? This isn't some time for a soliloquy, darn it.
The goals of rectan. You see, there are these seagulls on the island of Rectan who unwittingly discovered the fundamental theorem of calculus.
I really can't tell if you're messing with me.
Follow me. I'll explain it so even you can understand it.
All right, fine.
To the island of Rectan we go. Before we get to the fundamental theorem, we need to first review some big ideas in calculus that we already learned.
Okay.
All right, check out this graph. What do you see here?
We have a graph of sine of x. There's a delta y and a delta x for the secant line. Oh, and there's also a tangent line.
Right. Now, is the slope of the secant line the same as the derivative of f of x at x equals a?
No. We want the slope of the tangent line, not the secant line.
Right again. Why is f prime of a approximating delta y over delta x here, but not exactly equal?
Because the secant slope is close, but not exactly the same as the tangent slope. This is easy, Eggy. I thought you were going to help me with the fundamental theorem.
Patience, Red. You will see how all of this is connected to FTC soon, okay? Let me move point B, this blue point, closer to the other point as I zoom in. What important calculus concept are we demonstrating?
A limit?
Right. The y value of the blue point, B, is approaching the y value of the point at x equals a. But something else is happening. In the limit as delta x goes to 0, we can make the average rate of change as close as we want to the slope of the tangent line, which is the derivative at x equals a.
Okay, that makes sense.
Now, what if we want the tangent slope at every point on the graph of this function?
Oh wow, these are more steps than the Great Pyramid of Giza. But wait a minute, aren't these just secant lines for all the rise over run sections of a graph?
True. But we're going to apply the limiting process. As long as the function is differentiable, we can turn an average rate of change into the derivative at any point by making the delta x approach 0. Check it out by moving the blue point again.
That's pretty satisfying, not gonna lie.
So if the curve has a derivative value for every x on in the interval, that means the derivative is a function as well. Got it? Take a closer look at that function shown in the graph.
Uh-huh.
Let's just drop in a rectangle underneath each step, starting at the x-axis. We will define each rectangle to have a height of delta y divided by delta x, and a width of delta x, since that's how the steps are spaced.
Oh, okay. That makes the rectangle's height approximately the same as the derivative in that small interval.
You got it. When we string together all the rectangles, it creates a graph. As you mentioned, the actual derivative graph doesn't have all these steps.
Oh, but in the limit, as the width delta x approaches 0...
You're smarter than you look, Red.
Aw, thanks, Eggy. Hey!
The original function here is f of x equals sine of x. What's the derivative of this function?
The derivative of sine of x equals the cosine of x.
The rectangle model does a pretty good job of approximating the cosine curve, doesn't it?
It sure does. And it seems this should work for any smooth curve, not just sine of x.
Good observation. By the way, what is the area of the rectangle?
It's length times width, which means, in this case, the delta y over delta x times delta x. Huh. The delta x cancels out. So the area of the rectangle equals delta y length in the corresponding steps?
Right. Keep this in mind because we will see this idea come up later.
Oh, I was also going to say that they look a lot like Riemann sums used to approximate the area under the curve.
They sure do.
Wait a second. So is this like the fundamental theorem of calculus?
Not quite, but we're getting there. Let's talk more about the area under a curve. What do you see here, Red?
It's the area from A to B under the curve. Isn't that the definite integral?
You're a step ahead of me, Red. Keep your thinking cap on. Now, what are we measuring when the curve is below the x-axis?
Oh yeah, that means the area is negative, right?
You're on the right track. Technically, area is always a positive number, but in calculus, we are actually measuring signed area of a bounded region. So this definite integral gives a negative value.
Oh yeah, I remember that.
Now, how could you find the area under a curve like sine of x?
Oh, I just said it. Riemann sums?
Correct. We can use Riemann sums. Let's stick with our awesome rectangles.
Yeah, the rectangle area is easy, length times width.
And a finite number of rectangles doesn't usually give us the exact area under the curve.
Except in the limit?
Go on.
Sorry, I thought you were going to tell me.
Well, you're right about using a limit to define the exact area of a bounded region. This time, we use the limit as the number of rectangles approaches infinity in the interval from A to B.
So we have to add up infinitely many rectangles? Ugh.
Yeah, yikes is right. Look at how much work it takes just to calculate this definite integral using the limit definition for the area under the curve of f of x equals x squared plus 3x plus 2. It can be done, but let me tell you, it ain't no picnic.
You can say that again.
There's one other thing about definite integrals. Look at what happens when I move the right endpoint, b, along the horizontal axis. Point b is acting like a variable instead of a fixed point. Now, this is how we will write the definite integral. What happens to the area as x changes?
The area is changing. Wait, where did that t come from?
Well, we are using x as the input variable, so we can't use it as the label for the horizontal axis. So we will just use any other variable, like t. F of t is exactly the same graph as f of x. The only difference is how we label the horizontal axis. But the main point here is that we sometimes want to use a definite integral to define a function. We usually call this an accumulation function because we are accumulating the signed area as a function of x. For example, we could call this function capital A of x equals a definite integral. Okay, we're almost ready to meet the goals of rectan.
I got this, Eggy. Given a continuous function f of x, the antiderivative of f of x is some other differentiable function, sometimes written as capital F of x. The antiderivative function is defined as any function whose derivative with respect to x equals the original function. For example, the derivative of 1/3 x cubed with respect to x gives x squared. So if our original function is f of x equals x squared, then capital F of x equals 1/3 x cubed is by definition an antiderivative of f of x. As a matter of fact, the antiderivative could also be 1/3 x cubed minus 1, 1/3 x cubed minus 11, or 1/3 x cubed plus e to the pi. They're all valid antiderivatives of f of x equals x squared. That's because the derivative of the constant parts equals 0. So in each case, the entire derivative is still x squared. That's why we add a plus c when we name the antiderivative, to account for the infinitely many constants. And we can always check our answer by taking the derivative of the antiderivative in question and seeing if it does equal f of x as desired. The antiderivative function is really a family of curves that are all the same shape, except they're vertically shifted. The vertical shifting occurs because that's what happens when you add a constant c to a function.
You sure know your antiderivatives. Besides the point, you already understand antiderivatives pretty well. Make sure you remember that capital F of x is the antiderivative of the function f of x. It will come up again. Look, I see our destination up ahead.
Did you say that these gulls unwittingly discovered the fundamental theorem of calculus?
Yep,
This I have to see.
of course. Let's check out my friend's room and talk more about it.
Hey, I'm Polly. Polygon. Welcome on in. I was just laying out my observations about the fundamental theorem of calculus for my presentation before the committee of bird brains. Would you like to hear it?
That would be great.
It's exactly what we're looking for.
When we gulls first arrived on the island, our feeding ground had rectangular borders that stretched 1 kilometer to the north and half a kilometer to the east, making the area half a square kilometer. And as the seasons went on, we multiplied in numbers until we reached an equilibrium population density.
What did you all eat?
Crabs. A lot of crabs. Anyways, at the end of the year, when the full gull moon appeared in the eastern night sky, every gull in the flock flew to the eastern border.
The full gull moon?
It's a thing. Stop asking so many questions. All of the gulls would fly off to the east, and when they arrived at the eastern border of the feeding ground, we all lined up to be counted.
Wait, they counted themselves?
We still do. It's the yearly census. But they couldn't get a good count when they were all spread out, so that's why they lined up. Now the population density reaches an equilibrium of exactly 1,000 gulls per square kilometer every season. No more, no less. And when they all lined up on the eastern border, there were exactly 1 meter between each gull. So the length of the line that first season was 500 meters, or half a kilometer.
A half. The same as the area measurement?
Right. That's the interesting part. The measurement for area and length of the line were always the same number, with different units, of course. Half a square kilometer area and half a kilometer line. But the weird thing is that gulls have no clue about area as a concept, let alone how to measure it. They only really cared about how many were in the flock that season.
Hold on. What does any of this have to do with the fundamental theorem of calculus?
Patience, Red. You'll see in a minute. The next season, their feeding ground was a different rectangular region. And when they lined up, their length was 1 kilometer, same as the area measurement of 1 kilometer squared. So each season, the feeding ground was in the shape of a rectangle.
Why rectangles?
Because we are rectangles, obviously.
Good one.
Then one season, a strange thing happened. At least the gulls thought so. The northern border was slanted. The gulls populated the region until they reached their equilibrium density of 1,000 gulls per square kilometer. But on the night of the full gull moon, they were all confused about how to line up in their triangular feeding grounds, because they were...
Rectangles?
See, you're catching on. So, being good rectangles, they instinctively rearranged themselves into a rectangle formation before flying off to the eastern border. Since the triangular and rectangular regions both have the same area of half a square kilometer, their line was also half a length in kilometers.
So, the rectangle had exactly the same area as their triangular feeding ground?
Yes, they actually rearranged themselves to form a rectangle with a height that was the average value of the function on the interval. Don't ask me how, though. I flunked ecology.
That's crazy.
I know, right? Eventually, the northern border changed from a straight line to a curve. As was their custom, they formed the average value rectangle before flying off to the east. Then one season, something really interesting happened. They spontaneously formed 2 rectangles instead of 1.
Why did they do that?
Well, when the gulls tried 1 rectangle, many of them were flying outside of their feeding ground where it was dangerous. So they split up and formed 2 smaller rectangles to minimize the number of gulls in the danger zone.
Okay.
When it was time to fly off to the east to be counted, the gulls in the easternmost rectangle lined up on that rectangle's eastern border, while the gulls in the western rectangle lined up separately on their eastern border. Before counting themselves, the gulls in the eastern rectangle remained stationary while the western gulls flew to the north in a single file formation until the back of their line reached the northern edge of the other line. Then they counted themselves, as they had always done, starting with the eastern line and then the western line.
I still don't know how this has anything to do with the fundamental theorem.
Well, you're about to find out. Now that the goals had figured out how to form separate rectangles, they started forming more and more rectangles each season that passed and always flew to the north in a single file to make step formations before counting themselves. One day, there was this one gull named Gottfried Leibniz, who was fascinated by the way his kin has evolved to form rectangular counting patterns. Unlike all of the other gulls, he had the gift of being able to understand the concept of area and how to measure it. He also understood that the curvy northern boundaries could be described by functions with equations. It didn't take him very long to realize that the length of the lines formed by the goals in each rectangle was also a measurement of not only the rectangle's area, but also the area of the original subregions where the rectangles originated. And then he discovered that when the goals marched in formation to count themselves, they were actually measuring by accumulation the area of the original feeding ground.
Amazing. So each segment length represents the area of its respective rectangle, and when they're stacked up, the total length gives the combined area of the rectangles?
Which, by definition, is also the combined area of the enclosed region.
Precisely. He carefully studied the phenomenon and asked himself some important questions. What happens if the number of rectangles approaches infinity? Would a step-like accumulation pattern ever become a smooth curve, he wondered.
Oh, in the limit.
Now you're cooking, Red.
He imagined the eastern border as the variable x and investigated how the accumulated area changes as x changes. He wrote the integral function capital A of x on his whiteboard.
Oh, that's the accumulation function that we were talking about earlier.
Right, Red. Then he asked a really big question. If capital A of x becomes a smooth curve in the limit as the number of rectangles approaches infinity, then what is the slope of the tangent line evaluated at the point x? Shouldn't this accumulation function have a derivative at x? When he focused on the very last step of the accumulation step function, he realized that all of the pieces for calculating the derivative were right there in the last step. There was a fixed point, a delta y, a delta x, and a limiting process as delta x approaches 0. So he wrote down a prime of x using the limit definition of the derivative. And in the limit as delta x approaches 0, f prime of c approaches f of x. To his astonishment, after the substitution and cancellation, Gottfried could plainly see that capital A prime of x equals to f of x, which by definition means that the accumulation function capital A of x is actually the antiderivative of f of x.
Whoa. Are you telling me that the accumulation function is really just an antiderivative in disguise?
Yep.
But how did that f of c become f of x?
Well, just look at what happens in the last rectangle. In the limit as delta x approaches 0, the average value on the interval f of c gets squeezed closer and closer to the fixed point at x on the right side of the interval. In other words, f of c becomes f of x in the limit.
Oh, I see.
Now that you understand the Fundamental Theorem of Calculus, Part 1...
Hold up. What do you mean by Part 1? Just how many parts are there? Just as I thought I was getting the hang of it, you go on and drop this bomb on me?
It's okay. Just relax, Red. There are only 2 parts to the Fundamental Theorem of Calculus, and the second part is really a breeze now that you understand Part 1.
Now, Gottfried here went back to the drawing board and started to think more about the implications of the accumulation function being an antiderivative of the original function. He wondered, suppose I went to find the area bounded by f of x on a fixed interval, let's say from P to Q. Recall that the area of each rectangle in this region is represented by the height of each corresponding step. So, the total area of the region is simply the sum of the vertical step lengths inside the region. But now that we know that the accumulation function is the antiderivative of the function, it's no longer necessary to add up infinitely many parts. All we have to do is find the distance between capital F of P and capital F of Q, which is simply capital F of Q minus capital F of P.
Let me see if I understand what you're saying. If we can find an antiderivative function for f of x, then the definite integral equals capital F of Q minus capital F of P. And we don't have to even use the limit definition of the definite integral anymore?
That's right.
But doesn't this depend on which antiderivative function you choose to calculate f of q to f of p? After all, there are infinitely many antiderivatives.
Actually, it doesn't matter which antiderivative is used. You can see why by changing where the left endpoint, A, is located. This is equivalent to vertically shifting the graph with different c values. But notice that the distance between capital F of Q and capital F of P remains the same no matter where point A is located.
Oh, so it's because when you subtract f of p from f of q, the c doesn't really come into play in the final result.
Correct again. Wow, Red, you've come a long way.
Oh, now I see why the integral symbol is used for both definite integrals, which describe area, and the indefinite integrals, which describe antiderivatives. It's because we can use an antiderivative to find the area of a bounded region from P to Q, right?
I think so. Anyways, that's FTC part 2. I use P and Q for the interval, but you might notice that most textbooks use A and B. It doesn't really matter though, they're all just helper variables.
Wow, this all makes so much more sense now. Thanks, guys.
Oh, and remember how I showed you that we can drop in rectangles underneath the delta y by delta x steps in order to visualize the derivative function?
Oh, sure, I remember.
Aren't these also the same average value rectangles that the goals make and Goldfried used to model the definite integral?
Oh yeah, they do seem to be the same rectangles. Is that a coincidence?
I don't think so. Let's leave it as an exercise for the viewers to prove that they are the same.
It looks like everyone is here. It's about time we begin today's lesson. I hope everyone took their notes on the Fundamental Theorem of Calculus last night. Red, no sleeping in class. Red, wake up and tell us what the Fundamental Theorem of Calculus is.
Huh? Where am I?
Red, you're in math class, and I'm asking you to tell
Where
us
am I?
what the Fundamental Theorem of Calculus is.
Well, by definition, the Fundamental Theorem of Calculus says that the derivative of the definite integral from a to x of a function is equal to the function. But beyond its definition, what the FTC tells us is that if we graph the accumulation of an area of f of x as x increases, we get a new equation that we can call capital A of x. And if we differentiate this equation, we get f of x. So the accumulation function is also its antiderivative. From this, we can extrapolate that there is a second part to the Fundamental Theorem of Calculus. We can find the area under the curve between two x values a and b by simply substituting the values a and b into the antiderivative function and calculating the difference between capital F of b and capital F of a.
Well, Red, I guess you can go back to sleep because today's lesson is all about part 2 of the FTC.
Hey, I owe you one, Eggy.
Huh?